The function f is defined for x for all real numbers by fx is equal to x squared plus ax plus b, where a and b are constants. A. It is given that a equals 6 and b equals minus 8. Find the range of f. Notice that the function x squared plus ax plus b is a quadratic. For a quadratic with a positive coefficient of x squared, we know that the range would be bigger than the minimum point of the quadratic. To find the minimum point, we must complete the square for the quadratic. Substituting a equals 6 and b equals minus 8 into the function gives fx equals x squared plus 6x minus 8. 6 divided by 2 is equal to 3. Therefore, we know that it must be x plus 3 squared for sure, which gives x squared plus 6x plus 9. Therefore, we need to minus 9 to keep the value the same, and then the minus 8 follows on. After you complete the square for a quadratic, the minimum point happens when the square or whatever is inside the square is equal to 0. So this is when x plus 3 equals 0 and x equals minus 3. And the corresponding function value would be equal to minus 17, which is anything that's outside the bracket. And the range of the function would be function is bigger than or equal to minus 17, which is the minimum value. B. It is given instead that a equals 5 and that the roots of the equation fx equals 0 are k and minus 2k, where k is a constant. Find the values of b and k. From the first part of the question, we know that the function is equal to x squared plus ax plus b. In this part of the question, a equals 5, so the function turns into fx equals x squared plus 5x plus b. If the roots of the equation fx equals 0 are k and minus 2k, this means that if we substitute k into the function, it should equal 0. And when we substitute minus 2k in the function, it should equal 0 as well. So we can substitute k and minus 2k into the function and set them equal to 0. And now we have two equations in terms of k and b that we can solve simultaneously to get k and b. There are a few ways we could solve simultaneous equations. In this case, the coefficient of b is the same, so I will subtract the two equations to eliminate b first, and then find k, and then substitute that back to find b. When solving for k, we got two answers for k, which are k equals 0 and k equals 5. K represents the roots of the equation fx equals 0. If k was equal to 0, then the roots would be 0 and minus 2 multiplied by 0, which is just 0. Therefore, there would only be one root if k was equal to 0. Therefore, k does not equal to 0 in this case. For k equals 5, however, there will be two roots. One root is 5 and the other root is minus 2 times 5, which is minus 2k, and therefore this works, and k equals 5. Then all we need to do is substitute this value of k back into any equation and use it to solve for the value of b. And therefore b equals minus 50 and k equals 5. There is one other way we could work out the value of b and k. Using the fact that the roots of the equation fx equals 0 are k and minus 2k, and the fact that the function is a quadratic, we usually find roots by factorizing the quadratic. So if the roots are k and minus 2k, we should be able to write the quadratic as x minus k multiplied by x plus 2k. And those two expressions represent the same thing. They both represent fx, therefore they must be equal to each other. Because when you factorize a quadratic, you are just rewriting the quadratic, you are not changing the value. So therefore, when we expand the brackets, we should get the same thing back. Now, if you compare both sides of the equation, they look the same on both sides. They have an x squared term, an x term, and a constant term. Therefore, by direct comparison, the coefficients and the constants should be the same. By comparing the coefficient of x, k should equal 5. And by comparing the constant term, b should equal minus 2k squared. And therefore we have our value of k, and we can use k equals 5 to substitute it into b equals minus 2k squared to get the value of b, which equals minus 50, which is exactly the same as we got from the previous method. C. Show that if the equation f of x plus a equals a has no real roots, then a squared is less than 4 times b minus a. From the first part of the question, we know that fx equals x squared plus ax plus b. So if f of x plus a equals a, when we substitute x plus a into the function, it should equal a. The expression simplifies to x squared plus 3ax plus 2a squared minus a plus b equals 0. So if it has no real roots, then it has no solutions. The expression is still a quadratic because we have an x squared term and an x term and a constant term. Therefore, for quadratics, we know that it has no solutions or no real roots when b squared minus 4ac is less than 0. The expression might look complicated, but for this expression, a equals 1, b equals 3a, and c equals everything that is at the back, which is 2a squared minus a plus b. So substituting those values of a, b, and c into b squared minus 4ac is less than 0, we should be able to simplify and combine like terms until it turns into a squared is less than 4 multiplied by b minus a.